Other functions and their properties. First, we want to talk about domain restrictions. Now, so far, the domain of a function has been negative infinity to infinity, unless there is a restriction because of square roots or fractions. For fractions, if x is in the denominator, then we know that the denominator cannot equal 0. For square roots, if x is in the radicand, the stuff that's under that square root, then we know the radicand must be greater than or equal to 0. Or in other words, the radicand cannot be negative because we cannot take square roots of negative numbers. Now let's write the domain and the range of the function in interval notation. You may want to use your graphing calculator to find the range. When I'm looking at this function, I see there are no fractions and there are no square roots. So the domain is going to be all real numbers. And interval notation will be negative infinity to infinity. If we want to find the range, it'd be good for us to grab our calculator and see what this looks like in our graph. Y equals negative 2x. And when I graph this, I see it's simply a line. And the domain, of course, is negative infinity to infinity. When I read my range from bottom to top, it will also be negative infinity to infinity. Now looking at a graph like this, first of all I know the domain is from negative infinity to infinity because I have no fractions and I have no square roots. When I look at the graph of this, let's go ahead and put this in. We put in an x squared plus 2. I'm going to graph. We can see this parabolic shape, and if you want, you can trace or you can zoom a little more. You can look at the table. Let's go ahead and zoom in at that point that we see is at the bottom of the parabola. It looks like it's hitting a 2 right there. If we look at the table, we can see there is a bit of symmetry in the table there, and 2 is the lowest point for our y's. So definitely we're going to say that the range is from 2 to infinity. And 2 is a solid point, so we'll use a square bracket on that. Here I have the square root of x plus 1, so I'm going to have a domain restriction on this one. I know that the domain restriction is that x plus 1 must not be negative. In other words, it has to be greater than or equal to 0. So I'm going to solve this, subtracting 1 from both sides, and I get x is greater than or equal to negative 1. In interval notation, that's going to be square bracket negative 1 to infinity. Now let's see what happens when we graph this. We hit square root of x plus 1 and close your radicand. And then I want to go ahead and zoom a standard zoom, so I have my standard negative 10 to 10, negative 10 to 10 graph. So my domain I see is from negative 1 to infinity. The range is also going to start here. If you'd like, we can zoom in. Let's move the cursor so the cursor is closer to that point where we're starting. And it looks like it's starting there at a 0. We can even look at the table and see that at negative 1 we have a 0 for y. Below that we'll have error. So I know that my range is going to be a 0 to infinity and a square bracket on my 0. Now for this kind of graph there are no restrictions. We do have absolute values, but it's not a square root and it's not a fraction. So the domain, again, will be negative infinity to infinity. Let's look at the graph here. to enter this, what I'll need to do is put in an absolute value. So first, from the y equals screen, we're going to hit Math, arrow right so that you're in the number menu, and the first option is absolute value. And we're taking the absolute value of x minus 1 and close the parentheses. So it's taking the absolute value of everything after that that's in parentheses. Let's do another standard zoom. And yes, we can see that the domain is negative infinity to infinity. It looks like our range is probably from 0 to infinity. If you'd like, we can zoom in on that part of the graph, or we can look at the table. And definitely 0 is the lowest place on the graph here. So our range is going to go from 0 to infinity. Let's write the domain of the rational function in interval notation. Here I have a fraction, and I know that x minus 1 cannot equal 0. If x minus 1 did equal 0, then we'd have division by 0. So solving this gives me x cannot equal 1. If you'd like to see a graph of what this domain would look like, it's going to be everything on the graph shaded except for 1. So in interval notation, my domain is from negative infinity to 1, union 1 to infinity. For this rational function, I know that t squared minus 4 cannot equal 0. Then we'll go ahead and factor. And I get t plus 2 can't equal 0. T minus 2 cannot equal 0. So t can't equal negative 2, and t can't equal positive 2. If I look at that domain on the number line, and it's going to be open at those spots with parentheses, but everything else is okay. So I have 3 intervals that are being put together with 2 unions. So my domain in interval notation is negative infinity to negative 2, union, negative 2 to 2, union, 2 to infinity. Again, I have a denominator, so I know that the x squared minus 2x minus 3 cannot equal 0. So x minus 3 times x plus 1 cannot equal 0. X can't equal 3, and x can't equal negative 1. Again, if I graph the domain on the number line, I have everything shaded except for negative 1 and 3. So 3 intervals joined with 2 unions. So the domain in interval notation is negative infinity to negative 1, union, negative 1 to 3, union, 3 to infinity. A graph of a function is shown. Write the domain and range of the function in interval notation. So my domain, if you can imagine rolling a pencil across here, if you'd like, I can go ahead and draw a vertical line here, and I'm going to pretend this is a pencil. We're rolling it across left to right. So what is the first x value we see? The first x value we see is negative 2, and then all of those x's are touched until we get to positive 2. So my domain is going to be from negative 2 to positive 2, and with square brackets there. Let's do the same thing with a horizontal line to read our range. So we're going to take this horizontal line and draw it from the bottom to the top. Just roll your pencil from the bottom to the top. And the first y value that we see is -1, and it goes up to +3. So our range is -1 to +3. And of course, square brackets on those because the endpoints are solid dots. Now for this function, let's find the domain and range. The domain goes from -2, and everything is covered until we get to +3. Square brackets on both. The range goes from -2 up to +2. Another way you might picture this is if we would take this function and squish it all onto the x-axis. So what would be covered if we squished everything down onto the x-axis? -2 to 3 would be covered. And if we would take that same graph and squish it all onto the y-axis, what would be covered? Everything from -2 to +2. With this function, we know that the domain is going to be from -infinity to +infinity, much like one of the graphs that we did earlier. This was another squared graph that we did, and the domain was -infinity to infinity. So all those graphs are going to have a similar shape, and they'll have the same domain. Remember, there are no square roots and no fractions in that type of a function. So the domain here is -infinity to +infinity. Now my range, thinking about rolling the pencil up, the first number we touch is -3, and it keeps going to infinity. If possible, use the graph to evaluate each expression. Then use the formula for f of x to check your results. So first, let's find f of -1. So we find where x is -1 on the graph and follow down till we get onto the graph. That gives us a point -1, -2. So f of -1 is -2. And for f of 2, we're finding on the graph where x is 2. We follow up till we get onto the graph. We have the point 2, 1, which means f of 2 is 1. Now let's double check that with our formula. -1 squared is +1 minus 3 is -2. 2 squared is 4 minus 3 is 1. Again, let's find the function values here. F of -1. So we go to -1 and follow down to get onto the graph. We have the point -1, -2. So f of -1 must be -2. Then let's try and find f of 2. We go to 2 and we follow down till we get on the graph, and it looks like a -2 there. Let's double check with our formula. If I put in a -1, 3 times -1 is -3 minus -1 cubed is a -1. So that gives me a -3 plus 1, which is -2. Let's put in our 2. 3 times 2 is 6 minus a 2 cubed is 8, and 6 minus 8 is -2. So my work checks. Let's graph these functions, and it might be a good idea, if you're not sure what the graph will look like, to go ahead and make a table of values. For this one, let's go ahead and make a t-table. Let's go with integers from -3 to +3. Gives us a nice range of negative and positive numbers and 0. When I put -3 in this function, -3 plus 2 is -1, and the absolute value of -1 is 1. Putting in a -2 plus 2 is 0, and the absolute value of 0 is 0. If I put in a -1 plus 2, I get a 1. The absolute value of 1 is 1. A 0 plus 2 is 2. Absolute value of 2 is 2. A 1 plus 2 is 3. The absolute value of 3 is 3. 2 plus 2 is 4. Absolute value is 4. 3 plus 2 is 5. Absolute value is 5. Now we have these points that we can go ahead and graph. A -3, 1. -2, 0. -1, 1. 0, 2. 1, 3. 2, 4. 3, 5. Now what we have looks a little bit like a check mark. Let's say that we picked something over here a little further, maybe a -4 or a -5. What would happen? A -4 plus 2 is -2, and the absolute value would be a +2. Putting in a -5 plus 2 is -3, and the absolute value is +3. So I'd have a -4, +2, a -5, +3, and this continues. You can see we have this graph that's a V-shaped graph, and all of our absolute value graphs will have that same type of style. Now this one is a familiar graph. We have a line equation, so you can use just y equals mx plus b in order to graph this. Remember that the b is the y-intercept, and the m, the number in front of the x, is your slope. So I'm going to use first my y-intercept of 1, and then my slope is up 1, right 2. Up 1, right 2. Up 1, right 2. Now when you feel like you have enough points to draw a fairly accurate line, go ahead and connect those and make sure you're putting those arrows at the end of your line. Now for f of x equals 1/2 x squared, let's go ahead and make a t-table of values again. Let's say that we go through the integers from -3 to +3. So -3 squared is 9 times 1/2 is 9/2. -2 squared is 4 times 1/2 is 2. -1 squared is 1 times 1/2 is 1/2. 0 squared is 0 times 1/2 is 0. 1 squared is 1 times 1/2 is 1/2. And you'll start to see symmetry in the table there. 2 squared is 4 times 1/2 is 2. 3 squared is 9 times 1/2 is 9/2. Let's go ahead and graph these points. -3, 4.5. -2, 2. -1, 1/2. 0, 0. 1, 1/2. 2, 2. 3, 4.5. So you can see a nice outline of the parabola shape that we need. That does it for this lecture. Go ahead and try your homework and be sure to let me know if you have questions.